All right, we left off on 19, so we're going to pick right up on question number 20. Let's do this. Here we go. A sample of compound contains 7.89 grams of potassium. 89 grams of potassium. 2.42 grams of carbon and 9.69 grams of oxygen. Determine the empirical formula, which has a molar mass, empirical and molecular, which has a molar mass of 198.22 grams per mole. Okay, so we'll have to look at that at the end of the problem. All right, so if you're given mass or percent, what do you convert it to? Moles, that's right. So if you had like percentage signs, you would literally remove the percentage sign and just place a G for grams. And then once you have grams, start converting to moles. All right, so each one of these is going to be converted. Let's go. Because remember, formulas come from mole ratios. All right, be careful on potassium. Very common area to make a mistake. Round that to a tenth. And oxygen. All right, let's solve all of these and see what we get. They're not going to be pretty numbers, and we'll talk about what to do next. This is 0.20. If I round to 3 sig figs, it'll be 0.202 moles. This one will also be 0.202 moles. And let's do the last one. This will be 0.606 moles of oxygen. So you can kind of see how the ratio is going to be. It's probably going to be 1 to 1 to 3. But technically, what's the next step that we should be doing at this point? What if you had something where you couldn't tell what the ratio is? What are you supposed to do? Divide by the lowest number you got. So it's 0.202 in each case. This comes out really nice. This will be 1 to 1 to 3, which makes your empirical formula have 1 K, 1 C, and 3 O's. This would be your empirical formula. Okay, it's empirical because we can't simplify that down anymore. It doesn't simplify. 1 to 1 to 3 doesn't reduce. So at this point, what you need to do is go back to the problem and look at this mass. They said that whatever the compound is, it has this mass, 198.22 grams per mole. Let's see what this guy's molar mass is and compare. All right, so K is 39.1, carbon is 12, and oxygen is 16 each. All right, this guy has a molar mass of 99.1 grams per mole. See how they don't match? What do I do? They don't match. Are they supposed to? Well, maybe, but what do you think I should do now? Yes, ma'am. Yeah. We're going to figure out how many times this mass right here can fit into that mass over there. So basically, we're going to take 198.22, oops, sorry, 198.22, and divide it by the 99.1 just to see how many times it goes in there. And you'll realize it's about 2. What that means is that this right here, it may be the empirical formula, but it's not the molecular formula. In order to get to the molecular formula, we're going to have to multiply this whole thing by 2. All right, so how many K's do I have now? 2. How many C's? 2. How many O's? 6. All right, and that one right there, that's going to be your molecular formula. Can the empirical formula be the molecular formula? Yes, sometimes. You have to match the molar mass in order to confirm. All right. Excellent, that was 20. Let's do 21. Which compound has a greater percent by mass of chromium? All right, so this is 21. You're going to compare K2CrO4 versus K2Cr2O7. One of them is potassium chromate, and the other one is potassium dichromate. Okay? All right, so basically to figure out which one has a greater percent of chromium, we're going to do something called percent by mass. Sound familiar? All right, this is sometimes also called, I know, sorry. They're like, no, it doesn't sound right, doesn't sound familiar. This is also called, let's see, percent composition. Percent composition. It's basically, guys, this part right here is almost like percent composition, where basically you have these mass ratios. Down here, you don't have any masses. So all I gave you was formula, so how could you possibly get to a percentage? Just remember, percents, when you're working with them, it's always part, a small number on top, over the whole, the grand total on the bottom. So if I asked you to compare the percent composition of chromium, what's going to be on the top? Chromium. What's going to be on the bottom? The compound. Sometimes called Mo over Mach. Do you guys remember any of that? Mass of the element over the mass of the compound. All right? So we're comparing these two compounds over their composition of chromium. So first things first, I kind of need to have my masses, right? All right, so potassium is, let's see, 39.1 each, but you better double that up. Chromium is, let me check that, where are you? Oh, I see it, 52.0. And then oxygen is 16, right? But you've got 4 of them. Okay, so let's get the grand total first. 39.1 times 2 plus 52 plus 16 times 4. All right, the grand total is 194.2 grams. So let's get this first compound's percent chromium. I'm going to place chromium on the top, and there's only one chromium, so it's going to be 52.0 grams on the top. But the grand total, 194.2, is going to be on the bottom. And don't forget to multiply by 100. So 52 divided by the grand total times 100. I've got a percent of 26 point, and if you want to go to 3 sig figs, it'll be 26.8% roughly. Okay, so that's how much chromium is in the first compound. Let's compare that to the second one. This will still be 39.1 times 2. Chromium this time is going to be 52.0 times 2. And then your oxygen will be 16.0 times 7. Let's get the grand total here. Times 2. 52 times 2. 16 times 7. Okay, I've got 294.2 grams for the total. Okay. All right, so the second compound, percent chromium, will look a little different. Instead of saying 52 on the top, we need to say, 52 times 2. So I'm going to just do that real quick on my calculator. That gives me 104. So I'm going to place 104.0 grams on the top. The grand total this time is 294.2 grams. That'll be on the bottom, and times it by 100. Okay, the percentage now is 35, if you want to round to 4 sig figs, 35.4%. So, oops, I don't know how I just did that. That's awesome. 35.4%. So this bottom guy, the second compound, has a higher percentage of chromium. All right, makes sense, everybody? 21 was a good one. All right, let's do 22. Which gas will diffuse faster, chlorine gas or argon gas, and how much faster? All right, this is that effusion stuff again. Chlorine. This is a diatomic molecule. Remember Brinkelhoff, right? So his molar mass is 35.5 times 2. It gives you 71.0 grams per mole. Let's compare that now to the other gas, argon. Argon. Argon is a noble gas. Is he part of Brinkelhoff? No. His molar mass is 39.9 grams per mole. Without doing any math, can you tell me which one's going to be faster at the same temperature? Argon. Cool. So we have to figure out how much faster. And there's a special way to do it. And it kind of looks something like this. Rate is equal to, and then you do square root, and you got like molar mass A, and square root, and like molar mass B. And it looks something like this. Bottom line, you need to do some square rooting of the masses. Which mass do you want to place up on top if we're trying to figure out who's how much faster? The larger molar mass needs to go on the top. The smaller molar mass needs to go on the bottom, because all you're doing is trying to figure out how much faster. It's super easy. All right, so we want this rate, this value right here, to be a value that is greater than 1, because if I say I'm faster than you, I want that number to be a value greater than 1. You know what I mean? Like, I'm twice as fast as you. You would never say, I'm 0.5 times fast as you. That's stupid. Okay, you're actually slower. All right, so this number on the top is going to be 71.0. And the number on the bottom is going to be 39.9. Now I have some recommendations, because some students, they'll set it up right on their paper, and then they will punch it in wrong. So can you just do a quick little check on your calculator? I love parentheses. They will never like screw you up. It'll keep the order of operation correct. So open your parentheses, hit your square root button, 71, close the square root button, then hit divide and do the same thing. Open parentheses, square root button, 39.9, close your little parenthesis, and then equals. I don't know why, but some of you guys, your math is just kind of messed up, and I haven't quite figured out exactly what's messing you guys up. Order of operation, baby. All right, I get about 1.3. So what this means, and how you would say it, is the smaller one, argon. Argon is faster. How much faster? 1.3 times faster than the other gas, which was chlorine, Cl2. And that would be your final answer. Okay? 23. A sample of a sample of oxygen gas diffuses. Oh, this is when I actually taught students how to do the math. If you guys would like, you can actually cross off number 23. I did a great video many years ago. If you go back to my gas laws unit tab and you're just curious how this actually goes, I saved that video to show students how to do this particular math problem. So if you want to look back at that, that's cool. So once again, just want to make sure you heard it. Go ahead and cross off number 23. You do not have to do number 23. All right, so let's skip on down to 24. Ooh, fun, gas laws. All right, you have a 2.56 liter container held at 35.6 degrees Celsius and 4.8 ATM. What is the volume if the temperature changes to 84.2 degrees Celsius and the pressure changes to 2.1 ATM? You'll notice I kind of lined it up. Initials on the top, finals on the bottom. So this is a review. This should look really familiar. This is your combined gas law. Now, you'll notice in the information provided that they didn't say anything about moles, did they? Or mass, right? No moles, no mass. So whatever's not given to you in the problem, just take it out. And then there's your gas law. All right, so let's start with the initial pressure. Initial pressure was 4.8 ATM. Initial volume was 2.56 liters. That's all good. So atmospheres and liters, those are good units so far. What about your initial temperature, which is being held at 35.6 degrees Celsius? Is that okay to use in your gas law problem? No. Why not? Yeah, you guys, please, please, for the love of mercy, remember to change your temperature to Kelvin when you're using your gas laws. That is the #1 killer of your grades from the gas laws unit. Speaking from experience, looking at your work. That is the #1 thing that killed you. All right, so here we go. In order to convert to Kelvin, you're going to take your degrees Celsius and add 273.15. That might be something that you should add to your note card. Yeah? Yeah, that'd be a good one. That'd be a really good one. All right, let's see what it changed into. So we're going to say equal to We don't know the new volume, but we do know the new pressure. It was 2.1 atmospheres. Make sure that these two pressure units are the same, and they are. That's good. You don't have the new volume, so we're going to put our empty, unknown right there. But the temperature changed. 84.2, that's degrees Celsius, so you're going to do the same thing. 273.15. All right. Ooh, lordy Chad. Math. So, math sucks. I understand. I know you guys hate it. But what's the technique that I gave to you guys? And I was like, just do it this way. It'll work really nice. Yeah, it's called cross multiplication technique. So I'm going to take the information that's on the top of the left and combine it with the bottom on the right. And it'll look like this. 4.8 atmospheres times 2.56 liters times 84.2 plus 273.15. All right, so there's all of that. Let's set that equal to, and now we're going to take the bottom and combine it with the top of the right. 35.6 plus 273.15 times 2.1, and there's our unknown V. How do we get V by himself? Divide. All right, so let's do this. Whatever I divide on one side, oops, sorry, that's a 35. Whatever I divide on one side, you have to divide by the same thing on the other side, right? So I'm just writing this all in. Cancel, 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 cancel. But I got to do this. And 2.1. There. CV, all by himself. Look at all that math. Take your time. Remember, on a calculator, order of operation really does matter. So if I were you, I would just like overuse parentheses and just go nuts on parentheses or simplify somehow. Just don't mess up your math, okay? And let's see if I can get you an answer before we're out of here. All right, and I got an answer of 6.77. I'm rounding to 3 sig figs, which probably isn't correct because, oh shoot, I'm looking at the problem. You see this right here? Yeah, that looks like 2, and that also looks like 2. So maybe I should round this to 6.8, and that would be liters. All right, you guys, there you go.